we discussed on in the last lecture we talked about self compacting concrete. We will continue with that today, but at the end we will also introduce fiber concrete. So, outline of today's lecture would be some tests for self compacting concrete, its use, advantages, and then we will have introduction to fiber concrete. Just to remember what we did in the last discussion, last lecture, we said that water to powder ratio should be 0.8 to 1.1 by volume, something of that order. Total powder content ranges from about 400 kg per meter cube to 600 kg per meter cube. Powder, remember powder means cement plus even fly ash or any other inert material. So, all that constitute powder. Coarse aggregate content 28 to 35% of the mixed volume, and water content less than 200 kg per cubic meter. Fine aggregate content, it is generally higher in this one, 48 to 55% of total aggregate, and this was possible because of very high range or ultra high range water reducing agent. And this is, if you look at the plasticizers 1960, super plasticizer, basically sulfonated melamine formaldehyde and sulfonated naphthalene formaldehyde. They are actually 1970s, and then polycarboxylate ether, that was 80s and 90s. Some modification of this one through polymer modification in between, all that occurred, and all this led to our honeycomb structure that could be obtained from this polycarboxylate ether type, and this is what led to actually SCC. This is what led to SCC. This arrow shows this was led to SCC. So, this is the honeycomb structure, and we know that for this one, this because of the steric stabilization, it could actually disperse the cement grain more, and that is what resulted in this kind of concrete, that is self compacting concrete, self compacting concrete. So, this is what has caused this. We discussed earlier how the what is steric stabilization and the kind of PC, how do they work. This we have discussed when we talked of chemical admixtures to concrete. We are just reiterating the same thing a little bit more, and historically this is led to self compacting concrete. So, that is what we are saying, that it led to self rock concrete. And if you look at the rheology, plastic viscosity along this direction, yield shear stress along this direction, and you know the Newtonian fluid will go somewhere there, Newtonian fluid will go somewhere there, all right. This will be a linear line with yield shear stress being 0. So, flowing concrete should have lot of very low, flowing concrete will have very low yield shear stress, flowing concrete. Normal concrete lies somewhere there with some amount of yield shear stress and the viscosity being there somewhere, right. So, normal concrete will lie somewhere there. High strength concrete, they have more paste, remember, and therefore, they change the like the yield shear stress might be somewhere there to yield some of this range, right, depending upon of course their flow properties, and viscosity ranges varying from this to this. So, this is high strength concrete because their paste content is more, and pumping concrete should have low viscosity, low yield shear stress, and viscosity should be somewhere there, right. Now, why low the yield shear stress is, it can withstand some amount of yield shear stress. How? Because it can yield some amount of yield shear stress, because you will be pumping them. So, there is a pumping pressure, only thing it should remain cohesive and should not segregate. Internal pressure, disturb relative motion between particles should not be there within it. but must form a plug and then move. So, that is pumpable concrete. Or now self compacting concrete is somewhere here, flowing concrete. So, very little yield shear stress and viscosity ranges from here to there. So, viscosity ranges from here to there. So, that is where in the rheological scenario self compacting concrete's location is somewhere there, should have very little yield shear stress, should flow straight away. So, that is what is self compacting concrete. So, it lies here somewhere, it lies here somewhere, all right. So, the test meant for self compacting concrete. So, we actually looked into all the principles of self compacting concrete, what it is, why it becomes self compacting, etcetera, in the last lecture, and then continued a little bit now, and now we can look into the test methods meant for self compacting concrete. Obviously, since it is flowing, highly flowing, does not require any compaction. So, we can't use the conventional slump test or compaction factor test. Compaction factor will be nearly 1, practically no variation, because it will just fill in, and obviously we can't use VB test, which is meant for stiff concrete. So, this is actually VB time will be 0 in all the cases. So, therefore, you have to devise new test for this one. Several tests have been devised, there are a large number of them, and some of them have been codified in some codes, but it is still to be universally accepted single or 2 tests which would be suitable for self compacting concrete, its property, to at least define it as a self compacting one. There is no single test, or currently there are a large number of tests, and they are getting gradually codified. You remember the requirement of self compacting concrete, we said it should have filling ability, passing ability, flowability, and remain cohesive, and so on and so forth, segregation resistance, several properties we talked about. Now, there cannot be any single test by which I can determine all those requirements or all those properties. So, how do I measure, for example, resistance to segregation? And quantification is, of course, is still far cry. So, at the moment there is no quantification, but some empirical tests are being devised, and we will discuss some of them. So, one of the tests is U-tube test. This test is effective only in judging whether or not the concrete has sufficient compactability. Will it compact itself? It will not be able to judge the flowability to a great extent, or other requirements, segregation resistance. So, it will not be able to judge the segregation resistance and such thing. If the concrete does not have sufficient self compactability, we have to detect the cause, of course, and the mix proportion has to be adjusted. I mean, there should not be any void in the system, it should compact on its own. So, this looks for self compactability. How does it look? I have actually a U tube separated by a barrier, kind of a barrier, separated by a barrier, all right. So, this is the U tube, this is the U tube, and then there is this is a partition, and there is a barrier. Now, this is actually a gate which I can open. So, I fill in the concrete here first. Dimensions are of the order of around whatever is given, 660 mm and so on, 260 mm and those kind of thing. Dimensions are by and large given, 280 mm dimensions are given by and large, the dimensions has to fit in. So, this 280 mm, 680 mm and so on and so forth, and there is a gate which I can open. So, I fill in the concrete here, the obstacle, and this place there is a gate obstacle also, the rebars are there, reinforcement bars are there, the spacing between the reinforcements are there are actually 16 mm bars, and the obstacles are there. So, what you do is, followed from this, I just lift this up and allow the concrete to move from here, allow the concrete to move from here. Now, if it is self compacting, then this height should be same. So, if this is not flowing due to low flowability, if it is not flowing and it is because of the segregation, then it cannot be self compacting. So, this is too stiff mix, it is a stiff mix, does not move at all, does not move at all, very stiff due to low flowability. It is a stiff mix, not self compacting. So, the stiff mix, it does not move at all, only little bit it moves, and actually it is too flowable, that means might cause segregation. Water might have moved, but the solid might have got stuck here, solid might have got stuck here, and thereby resulting in higher densities of the solid at this place, and only water flowing down there, solid remaining sort of kind of accumulating here, and therefore, it is not self compacting. Therefore, it is not self compacting. A self compacting one will have water, of course, if I put it, they will have, it will adjust, it will just have two equal heights, but this is not water, but it should be sufficiently close to each other, sufficiently close to each other. So, this is called U tube test. So, this test gives us self compactability, but slump flow gives us fluidity and deformability. So, two other tests, one is a slump flow test, other is a funnel test, have been proposed for testing deformability and viscosity respectively. So, therefore, fluidity is determined by slump flow. The criteria to satisfy self compacting concrete by slump flow test should be 64 to 75 centimeter slump flow. IS 456 200 456 2000 of course defines 600 minimum flow to satisfy it as a self compacting concrete, right. So, this is actually determines fluidity. Now, how does it do it? I will come to this. This is your slump cone, and these are the marking. This is about 500 and then if you fill it in the standard manner, and as you fill it in, lift it up, it should get spreaded like this. Measure the spread, measure this spread. So, this spread is a slump flow, and this flow minimum should be 64 to 75 centimeter, from 20 centimeter to it should go to about 64 to 75 centimeter. IS 456 says minimum it should be 60 centimeter or 600 millimeter to define it as a self compacting. So, minimum for self compacting concrete is given. But if it is less than 64 centimeter, then it is highly viscous concrete, and if the spread is less, lower down, that means approaching normal concrete. So, spread should be sufficiently large. So, therefore, its viscosity is high. Viscosity has a tendency, if it is lot of resistance, then it will not flow. So, it is somewhat measured, it is related to fluidity of the system, fluidity of the system. So, that is what it is, the slump flow test, and this is very popular because it is an easy test. B funnel test, it gives direct measure of viscosity, sort of it gives some direct measure of viscosity, that is what is people felt, and you have a funnel which is closed at the bottom in the beginning, and open the gate at the bottom, fill it in a standard manner, then the time is measured for discharge of the concrete through the bottom opening, which is now initially closed, and then it comes down here, and if this time is 10 seconds, 10 plus minus 3 seconds, then you can say it could be self compacting. So, basically you determine the fluidity, and this determines viscosity. So, this determines a measure of viscosity, this is a measure of viscosity. So, higher flow means what? I mean, if it takes longer time, that means a stiff concrete does not have flowability, is not proper, because it is flowing through that bottom opening. So, kind of viscosities would dominate. So, if you have too much of friction or viscous resistance, then it will take longer time, and if it takes too less time, maybe this it might have a segregation tendency. So, therefore, that is why it is 10 plus minus 3 seconds time. That is what is B funnel test. Now, segregation resistance is measured by L box test. This is segregation resistance measured by L box test. The vertical part of the box is filled with concrete, which is left to rest for 1 minute, During this time, the concrete will display whether it is stable or whether there is segregation. That means, when you keep it 1 minute in a vertical part of the L box, which we will see just now, if you leave it for some time, if there is too much of water segregation, it will come up. So, if it is not segregating, then you open the gate, as we shall see that, you open the gate as we shall see that, right. So, it will look like this. So, this is the L box. So, you fill it, there is a gate here, you close it, there are obstacles here, bars here. So, gate remains closed and fill in the concrete in a standard manner, be there, keep it there for 1 minute or so, and if there is no segregation, you allow it to pass through, you can judge whether segregation or not, then open the gate, it will pass through this obstacle and fill in the concrete at this portion, it will fill in the concrete here. So, it will look something like this, through the obstacle it will pass. 200 mm is the width of this one, these obstacles are 12 mm bars at 46 mm spacing, as a rate of 46 mm center to center spacing, and as it pass, the concrete here would be like this, and this height we call it as h 2, this is h 1, this dimension is 760 mm, this is 600 mm and so on so forth, and this is 150 mm. So, allow it to pass through it, and if this two h 2 and h 2 by h 1 is equals to 1, then it is perfectly self compacting. The water would actually make these two height same, but for self compacting concrete this should have a minimum ratio, that ratio is 0.8. So, that ratio is 0.8, that ratio is 0.8. So, it should be at least 0.8, at least 0.8. So, it should satisfy the criteria, satisfies SCC should be h 2 by h 1 should be at least 8. If it is 1, that is very good. So, it should be 0.8, it should be 0.8, it should be 0.8. So, that is what it is. So, this is another test. So, you can see there are several tests so far we have looked into, and there are more tests actually. For example, Sieve segregation test. Now, the problem is we are yet to actually we are yet to find out first of all the criteria, right, like we said, filling ability, passing ability, compactability, segregation resistance, fluidity, all this, there are several requirements. So, if you could, how do you quantify this requirement? Actually, to quantify the requirement, some sort of test should be devised, all right, and but then they are not all independent, because if you have high fluidity, maybe that will help in compactability. If you have for example, passing ability, that might have again related to flowability. So, there at the moment there is a kind of no uniformity. You see, when you are very confident about certain things, when understanding has grown very well, you need only one test or maybe one parameter to define everything, one model at least to define everything. But here the confidence is yet to build up on the understanding, and single tests cannot, right now there is no single test. So, there are several tests, as I said, suggested by different people, and finally possibly over the years it will come into a kind of now less, it will get reduced down somewhat. If one wants to look from fundamentals like Bingham's model, then this should have been Bingham's model, then this should have been the gamma yield shear stress and the viscosity, you call it nu or mu or whatever it is, you call it mu. So, this could have, viscosity should have been sufficient, but at the moment this is not really happening that way. For example, we said that gamma versus viscosity, if you plot it somewhere here it should lie. So, if there is no way to measure gamma, I mean there is no I will say not really no way, there is no universally accepted method to measure gamma or mu, the rheological properties. But supposing we could have done this, we would have said that for being self compacting, only one measurement, the rheological measurement determine gamma as well as mu, and you say if the gamma and mu ranges between this range, gamma should range from 0 to something, mu should range from this to this, then I will call it self compactible. But at the moment we are not at that stage. The way to measure this self compactibility is still not really universally acceptable, and neither the rheological properties, no universally accepted method for measuring rheological properties. I mean, rotation viscous meters are there, which we talked about, the tau versus RPM, etc., etc. Remember we showed some graph earlier when we were talking about rheological properties. So, these viscometers themselves are not really so far universally acceptable. All right. So, therefore, we have large number of tests. So, we have one more test, that is Sieve segregation test. Now, this test, it measures segregation resistance. Now, what you do? You allow the concrete to stand in a bucket for 15 minutes. 4 two dimensions of this system will be fixed actually. Pour top 2 liter on the sieve of 4.75 centimeter, 4.75 millimeter, it can't be centimeter, 4.75 millimeter, 4.75 millimeter, 4 centimeters will be this, 4.75 millimeter, sand size, it is a sand size, that is a mistake. So, with a pan below, ratio of the mass passing to poured mass is a measure of segregation resistance. So, what you do? You take the top 2 liter from a bucket, put it onto the sieve, and the amount passing through that sieve is a measure of segregation resistance, because you have kept it for 15 minutes. Now, if there were segregation, for example, if the water is coming out and the solids or larger particles etc., go down below, then actually quantity passing through this sieve will be very large. So, if the solid, even the finer solid is separating out along with water, it is taking out the finer material too much, then passing through 4.75 mm sieve, most of it will pass through. So, the quantity that is passing is a measure, quantity or proportion of the mass passing is a measure of segregation resistance. If it is less, that means the relative proportions of the fines water to the total mass, that would be, that should be appropriate. So, you can actually relate this to the segregation resistance. So, one can relate this to the segregation resistance, 5 to 15% is considered satisfactory. Less than 5% is high resistance to segregation, because nothing is passing, and more than 50% is possibility of segregation. So, less passes through it. First of all, you have separated out, taking only top 2 liters from the top. So, if it contains a lot of fines, and not larger material, but supposing it is not segregating, larger materials also will be here. So, if you take the top 2 liters, larger materials, so it is not segregating it, right, resistance to segregation. So, high segregation resistance might reduce down the flow, that is why less than 5% may not be desirable, but if more than 15% is passing, that means it contains mostly the fines, and therefore, majority is passing through it. So, therefore, this is a measure of segregation resistance, then this is another test, T50 test. I already talked about L box test. Okay, some more tests we will talk about. T50 test is time for 50 centimeter slump flow. So, you find out, measure flow as against time, measured flow against some flow against time, with time how slump flow is changing. So, time at which 50 centimeters slump flow occurs, that is T50 test. So, that gives you T50 test. So, that is again that is a measure of slump, in a way slump retention, it will be a slump retention or related to, it is another test actually. J ring test is slump flow with a ring obstacle. So, you have the same slump flow, but there is an obstacle, there is an obstacle, there is an obstacle, there is an obstacle. So, there will be obstacle here. So, it is a J ring test. Slump flow ring obstacle provides information of passing ability. So, whether while flowing, it is actually trying to combine the fluidity with passing ability. It is trying to combine the fluidity with passing ability. So, then you can find out the flow. After putting the obstacle, what is the flow? So, that would be a kind of measure of fluidity plus passing ability. Fill box test, that is again a box in which concrete is filled in first, then it is allowed to move through a number of obstacle, reinforcement bar, etc., etc. In the J ring test also we had reinforcement bars or bars making the obstacle through which it has to flow. So, this has also talks about it is a box through which concrete is again allowed to pass, and passing ability, since the obstructions are there in form of bars, right. So, this is also is a measure of passing ability. Well, there is a number of other tests. As I said, since we are still not in a state to finalize only a few set of tests, maybe 1, 2, 3 or 4, or maybe 2 tests or 1 test which can measure all the properties. It may be difficult at the moment to measure 1 test, but 1, 2 tests, empirical tests. Therefore, there are a number of other tests. So, a lot of people have developed a lot of tests, and this is what the state of this is the status. So, we discussed some of those tests. We do not have Indian standard, but there is an European one. So, EFNARC is a European one, guidelines 2005, this was available, and it includes some of those tests that I just talked about. Then Japanese standard for civil engineering 1998, they developed some of those tests. At the moment, Indian standard only talks of 600 slump flow. So, the status of the tests are here only. SCC for various applications. Depending upon the application, you will require viscosity from low to high, slump flow from lower to higher, and passing ability to segregation resistance. Passing ability to segregation resistance, all right. Segregation resistance, some cases you would require segregation resistance, should not segregate, somewhere it should have passing ability. So, the kind of some guidelines are available, for example, ramps where concrete can slide down, you do not want very high viscosity, So, it should be lot of resistance to movement, it should be kind of sticky. So, therefore, ramps you have low viscosity, lower slump flow, flowability also you do not need very much, but you need a lot of passing ability in this zone, you need passing ability, all right, passing ability. And floors and slabs, tall and slender structures, you need low flow, low viscosity, but high flow, tall slender structure and also passing ability, because you might have slender structure, a lot of reinforcement. So, flow could be, you need lot of flow, and therefore, should have passing ability as well. This will be part of floors and slabs, can be floors of slab, thin floors, thin slab, but larger floors and slabs which are flat, you might require segregation resistance to be specified, and depending upon the situation might require higher slump flow or lower slump flow. There are more to this, but I think I have just picked up some of them, and in fact, this just to explain, this diagram is a little bit high up, it could be somewhat down as well. So, for example, floor slab might it is okay, but it explains that I should have floor slabs, ordinary floor and slabs slightly thicker, could have very low viscosity to high viscosity, high slump flow. Of course, the viscosity is somewhere there, and segregation resistance could be there, but in some other thin structures, thin floor and slabs, it will be like this. So, these are the, this gives us some idea where for what kind of application what we require. There are many more like this. So, this is just simple, a few of them are shown here. Mixed proportioning, water to cementitious ratio from strength. First of all, you must determine water to cementitious ratio for strength. So, this is from strength criteria, because that would govern the strength. Best combination of C plus pozzolana or any other material that you are able, you can use a test called Punke test, used for cement fly ash, because this uses you find out the best packing density that is void at saturation situation. So, what you do, you mix C and P, that is your cement plus other powder material, in the proportion that you like, which will vary, maybe start from 10, go to 15, 20%, etc., etc. You add them up together, mix 90%, 10%, 85%, 15%, 80%, 20%, and so on and so forth. So, different proportions you can take, and then mix for a specific case of 90 cement, 90 cement, 90 cement plus 10 P. So, this is C and this is P plus this P 10. For specific combination, what you do? You put them in a container, measure their mass, etc., by various kind of several masses, empty container, mass with cement, mass with powder, other powder material, and so on. So, you add proportion, add them up in correct proportion, add water to the system and remove all voids to find out in the saturated state what is the void content, right. Void content, what is the saturation state, what is the void content, in the saturated state what is the void content, how much water has gone in actually by various mass measurement, and there is a formula available. Then next change it to 85 plus 15 and do this test. So, void content in each stage you can find out, and if you know the void content, overall volume, total volume, because mass of the materials are known, their specific gravitas are known, total voids, total volume of the solids you can find out. So, volume of the solids and volume of the voids are known, therefore, you can actually find out packing density, you can find out packing density. So, this Punke test can be used, which is actually used for fly ash cement combinations. So, you can use this test for finding out the best packing density for cement and powder, and that combination you can use, for your self compacting concrete. Packing density of aggregate you can measure, which we have talked about. So, paste volume would be void volume plus required slump flow. This is an empirical formula developed at IIT Madras, actually IIT Madras, they have developed this, but the equation may be different, but the idea is that paste volume is void volume plus how much paste, extra paste you need. It would depend upon required slump flow, but then they found it out to be required slump flow in millimeter minus 321 divided by 4. They found it out to be like this. So, for example, if this is about 640 you need, so, or 621, let us say for simple case. So, 300 divided by 4, void volume 300 divided by 4 must be expressed in terms of the volume in some cc or whatever it is. So, this will be 300 divided by 4, whatever, this is a empirical formula. So, the all I can say for at the moment is that it will be required depend upon the slump flow. Higher the slump flow required, more is the paste volume required, and this we have understood from the fundamental, because it is the paste on which the aggregates will have a kind of a piggyback ride onto the system. Therefore, it is proportional to slump flow. Higher the slump flow required, you will require more paste. The equation of course is empirical, so the units etc. are to be seen, but this equation may not be universally valid. Found out in one case, might somebody else might find out somewhat different these values and so on, but at least qualitative understanding is very clear. Void volume plus, if you require more slump flow, more fluidity, then you would require more paste, and this is understood. This is understandable from our discussion in different lectures, this is understandable. Superplasticizer doses are optimized by mini slump test, which we talked about. So, 170 spread and no bleeding, that is what gives us superplasticizer dosage. First you find out the compatible superplasticizer, you can do mini slump test or Marsh cone test or whatever you like, as we discussed earlier, and this is the guideline given that SP dosage would be 170 spread. So, this 170 spread is what they have actually suggested, but it could be different, but more spread with no bleeding. From this actually mini slump test you can determine what is the SP dose required. Viscosity modifier if required, there is a test, marble test, which is used for viscosity modification, whether how much quantity of viscosity modifier you need or do you need it at all. The viscosity modifier, which I did not mention much actually, is required to make if there is to reduce down the segregation, improve the segregation resistance. What will happen when you are adding too much of water and too much of adding the superplasticizer, hyperplasticizer, whatever they are, they would have a tendency to actually cause excess dispersion, and therefore, the water might get out, may not remain, may not be within the system. But if you have sufficient fines, very fines, the powder material, then it still may be holding it, particularly fly ash etc., which increases the cohesiveness, can hold it on together, and internal separation of the, it will provide resistance against internal separation of the particle, that is particle to particle distance within the whole system of concrete, larger particle to larger particle, they will not, relative motion would be minimal while flowing. But supposing this is not happening, then you can use VMA, viscosity modifying agent, which are nothing but we said that they would actually increase the stickiness, kind of glue, they will try to increase the stickiness, and that is what we have seen for underwater concreting also use VMA sort of thing. And when we talked of admixtures, we talked about this viscosity modifying agent or viscosity modifying agent, they are there. So, you might use them. Now, how much quantity you want to use and what you want to use, or whether you want to use at all or not, you can actually find out from a test called marble test. Other tests for self compactability, and then of course, you have to do trials. So, there are several tests, all those tests, YouTube tests etc., you can also do in addition to doing this kind of test, and then do the trials to see that it is self compacting. So, laboratory to laboratory they will actually select the test, but this is a kind of a guideline one can use for mixed proportioning as a simple way. This is from strength C plus P powder combination from Punke test, packing density that you check for aggregate, then superplasticizer dosage may be from mini slump test, with viscosity modifier application if required from marble test, and other test if required. So, what are the advantages? The advantages of obviously first is speed of casting. If it is self compacting, you do not require vibration, the speed of casting will increase. Less labor, that is of course, is an advantage in western countries, because as I told you, first it came from this for these two purposes, no noise and less labor, cutting down onto the labor cost of vibration. So, cost of vibration, use of vibration is actually cutting down on that, but then cost of the self compacting concrete will be somewhat higher than normal concrete, but if it is cheaper, putting together the labor cost, which I am not sure in Indian scenario how does it work, but even it must be working pretty well, because this has been self compacting concrete has been actually readily taken up by the construction company, and several projects actually have been have used actually this. For example, first one temple in Chennai, then the Delhi metro, it has also used, and there are several other places this is being used at the moment. So, the total cost must be, there must be cost saving must be there in terms of labor saving, although the self compacting concrete itself must be slightly costlier. Better compaction, surely better compaction, and of course, no noise. So, vibration noise would not be there, this is an advantage. Cost saving can come, because this saving would be there, saving on this would be there, right, cost less labor, and even saving on vibration machineries, compaction machineries etc. Better surfaced and as I told you, it is used in India in many sites, many sites have actually used this self compacting concrete. So, self compacting concrete has been used by in India by many sites. Well, there may be, let us see the properties. Strength, like normal concrete, that is non self compacting concrete, there is no really impact on strength really significant, but maybe higher. So, strength is like non self compacting concrete, because finally it is the water to cementitious ratio or water to cement ratio which you are using as a criteria that governs the strength. Therefore, self compacting concrete, it will be as good or as bad or as you design, maybe higher, slightly higher, because for better compaction. There should not be any question on tensile strength. It will be similar as non self compacting concrete. After all, we have seen that empirically tensile strength is related to the compressive strength. So, therefore, there is no question. Modulus of elasticity may be slightly lower because of higher paste content. Now, here is the modulus of elasticity. We talked about E of the concrete is a function of E of paste, paste volume, and E of aggregate and V aggregate. So, since I am increasing V paste and E paste, it will depend upon E of the paste. So, it will depend upon the situation where E paste is high, that means in a high strength situation, if you have self compacting, then modulus may not be lower. So, it will depend upon what is the E of the paste that you are using. So, it could be affected somewhat, right, slightly lower, higher paste content depending upon E of the paste. Might have slightly higher creep due to paste, because paste is responsible for creep, shrinkage, etc., etc. So, could be slightly higher because of the paste requirement. Shrinkage may be same kind of situation might be valid here. Drying shrinkage, if it dries out, then drying shrinkage, chemical, non autogenous and all those shrinkage, they may be similar as the non self compacting concrete. After all, here of course, it is related to the permeability of the system. Now, if there is something similar, water cementitious ratios, all these are similar, then it would be similar as a non self compacting concrete, but the paste volume is more. So, if the paste, whatever paste volume, whatever properties are affected by paste volume, this will also be affected by the paste volume itself. So, better bond strength, more paste could give you better bond strength with the steel. Fire resistance will be similar to non self compacting concrete, and durability may be slightly better than better surface because of the better surface concrete. Since surface may be better, it may lead to, because we have seen the durability is related to surface concrete, durability is related to surface concrete, all right, near surface concrete, and therefore, this may be slightly better. So, no significant difference with the non self compacting concrete in the properties concerned. Most of the properties will be similar, and it has been, that is why it has been readily acceptable by the construction industry. Unlike many other new special concrete which are specific application oriented, but self compacting concrete has been actually readily acceptable. I think the signature bridge in Delhi, which is being constructed now, is also another example where self compacting concrete is being used. So, self compacting concrete has found its use in many places. Popularity, the costs, the cost effectiveness is very much there in this particular concrete. So, but it needs a lot of understanding, development of still a lot of understanding is required in terms of its fundamental understanding. So, that is what is self compacting concrete. One can of course discuss much more about it in terms of the test methods that has been devised, because as I said, if it is all universally acceptable, then there will be less number of tests. but at the moment there are our understanding is yet to develop as far as behavior, I mean self compactability etc., are concerned. Therefore, you have large number of tests and one could have covered more, but then our time frame is limited, and therefore, this is what we can discuss, we can just conclude our discussion on self compacting concrete. So, the next special concrete that we look into is fiber concrete, fiber reinforced concrete, which I will introduce today and again continue with the next lecture. Now, fiber reinforcement has been used for many long time, for many years together in materials. For example, you use with mud, fiber reinforcement with mud plus fiber in making idol, to avoid shrinkage, crack, to avoid shrinkage cracks, drying shrinkage cracks. This has been there for many years, or similar other material, you put fiber to actually which can erase the cracks. Therefore, fiber has been used for many years, and in concrete also it is relatively older compared to other concretes that so far we have discussed. It is older, much older, because it has been used extensively in tunnel lining and such places over the years. So, let us look at where it is used, where its utility. Now, when we are talking of fiber or fiber reinforced concrete, we are essentially talking of short randomly oriented discrete fiber. These are randomly oriented fiber, just basically randomly oriented fiber. They are not aligned. I mean, you can align them, if you do, then it will be very good. For example, slurry infiltrated fiber reinforced concrete could be, you can have fiber aligned, or if it is long fibers, you can even align them and possibly make a mat out of it. That is a different one, but quite commonly used is short randomly oriented discrete fibers. That is what we are talking of, and they are conventionally different than conventional reinforcement, which we normally understand in concrete. They essentially improve the crack arrestation property. Pseudo ductility they would provide. How they will provide, we will look into them. Flexural strength enhancement is there, and obviously, they do not improve the workability. They are like elongated aggregates, and therefore, they lower the workability, and it will depend upon L by D ratio, bleed resistance, but provide better bleed resistance. So, we will come to each one of them, but just to understand this material, let us look at it. Obviously, they will have high cement content, MSA is low, and why this, all this we will look into. So, that is the characteristics of fiber reinforced concrete. So, let us say this is your concrete, and you have discrete fibers like this are the discrete fiber. So, when the crack comes, they will actually bridge the crack. When the crack comes, they will actually bridge the crack, and that is how they provide crack arrestation property. So, that is the understanding, or where fiber, the utility of the fiber, or how fiber, where fiber improves. So, we can now look into some details, but before that we can quickly look into some theories which we will discuss a little bit today. Supposing this is your material, that is your matrix as we call it, concrete matrix, and I have put some aligned fiber there. Now, I apply a tensile load, on both this direction, Now, actually material is in parallel, materials are in parallel, P load I have applied. So, part of the P will be shared by, there will be same strain will be same, epsilon will be same, long aligned fibers under tension, that is what we are looking at, over a small element, it is a small element, let us say. Fiber and matrix have same strain, because they are bonded together. So, we assume that there is no slippage, they bond together. So, load P is the sum of the load carried by both fiber and matrix. If I say V m is the volume of the volume fraction of the matrix, then fiber volume will be V f, and V m is equals to 1 minus V f. So, V m is equals to 1 minus V f, V f is the volume fraction of fiber, and modulus of elasticity can be simply written as composite modulus of elasticity can be simply written as V m E m and B f E f. How it can be written simply? Because strain is same, the strain is same, and one can actually show that the tensile strength of the composite will be proportional to fiber strength of the stress in the fiber and stress in the matrix, volume of the fiber, volume of the matrix. Okay. We will come to this actually in details, but just for the understanding, next class we will start from here actually. Again continuing with the same, for short randomly oriented discrete fiber, we will just come to the previous discussion in the next class. So, we can start with actually long aligned fiber in an element, derive their properties, long aligned fiber in an element in under tension. First we are starting with tension, because it is the crack arrestation property which is very important. So, fiber actually bridges the crack, and therefore, under any pull which causes cracking, it arrests this. So, to understand that, it is better to first look at an element with aligned fiber, and properties of aligned fibers are like this. I will come to this in detail in the next class actually, but right now just introduce it to you. So, the modulus of elasticity of the composite we can find out, modulus of elasticity of the composite we can find out, which will be a function of the modulus of elasticity of the matrix, that is your concrete, and the volume fraction of the concrete, and volume fraction of the fiber, and modulus of elasticity of the fiber under this kind of loading situation. Similarly, the tensile strength of the composite or tensile stress in the composite at any moment of time will be given by this. You can understand this of course quickly if I can look into sigma C t into A, total area. If this is the total area, A must be equals to, that is the force, is equals to P, and that must be equals to sigma matrix stress multiplied by the area of the matrix plus sigma fiber into area of the fiber. Now, since the lengths are same, this aligned fiber lengths are same. So, multiply everything with L, multiply everything with L, multiply everything with L. So, I can write sigma C t V is equals to V m, volume of the matrix, V dash of the matrix, and into sigma m plus V dash f of the matrix into sigma m. Now, V m dash divided by V m, I am saying V m dash divided by V is equals to V m, that is volume fraction. So, where volume fraction, and similarly, so this is how this equation is obtained. This equation is obtained. Now, since the strain is same, since strain is same, stress by strain. So, I can divide sigma C t by epsilon, which is same, V m by sigma m by epsilon, strain in all of them same. So, epsilon m I can write, this is epsilon composite, everything is same, plus V f sigma f by epsilon f, because epsilon m epsilon f is equals to epsilon c composite, and therefore, this they are same, and this is nothing but stress by strain is modulus of elasticity. So, it is a simple equation, one can easily derive it, right, one can easily derive it, and but then when it comes to random fiber, then what you do? You add some factors, because all the fibers will not be effective, they are not aligned. So, there will be kind of an orientation factor nu o, and length of all the fibers will not be full length. So, there is an equivalent efficiency factor, length efficiency factor. So, we call this as orientation efficiency factor, length efficiency factor, and composite strength, composite stress, then we can determine in this manner. Similarly, modulus of elasticity also we can look in this manner, and this is called length efficiency factor, this is called orientation efficiency factor, and next class we will look into the same. So, this is the introduction. So, therefore, today what we looked into? We looked into some aspect of SCC. Now, what is the aspects of SCC? We looked into tests today, but the principle basic mechanism by which actually we form SCC self compacting concrete we discussed in the previous lecture. Today we discussed about a little bit about the VMA what you call the superplasticizer which made it possible, a little bit about little bit about the principles of self compacting concrete, then the tests, their application, usage and advantages, etc. we looked into today, and then we just introduced the fiber concrete basic what it does actually, where its advantages like crack arrestation, pseudo ductility, flexural strength, and then we just try to introduce the theory of fiber reinforcement, assuming a element in which all fibers are aligned along the direction of load. We will come back to this in the next class and discuss the fiber concrete in the lecture 4 of this module 9. Thank you.